Hey, what's going on guys? Today let's talk about the Smith chart. Hey guys, in today's video we're going to take a look at the Smith chart. Most of the instruction in this video is given assuming you understand basic transmission line theory. On a lossless transmission line, the phasor voltage can be modeled by this expression where we have a forward propagating wave plus a reflected wave. So how much the wave is reflected by some load is determined by the reflection coefficient at the load, gamma sub L. Gamma sub L is a complex coefficient equal to the reflected wave divided by the generated wave. This means that the magnitude of gamma sub L must be less than or equal to 1. You can never get a bigger reflected wave than your original wave without using some sort of active circuit component. Now, I'm not going to derive this expression, but the reflection coefficient can also be defined by this ratio of characteristic and load impedances. This is why gamma is often complex. So, in order to process these real and complex values, we use a graphical tool called the Smith chart. In order to understand the Smith chart more fully, let's take a look at a typical complex plane. Because we are only going to be working with positive resistance, we only focus on the right half of the complex plane. On this plane, we can graph any impedance with a real and imaginary part, as long as our real part of Z is not negative. In this plane, the top half of our graph represents inductive reactance, while the bottom half represents capacitive reactance. The horizontal axis is our resistive axis. Now, if we curve our imaginary axis into a circle, we can see how the Smith chart gives us a circular way of looking at the same impedances. So the Smith chart can be a bit daunting at first, but let's break it down into smaller pieces. The origin, often called the prime center, is where the characteristic impedance of our transmission line is represented. We normalize our load impedance by dividing it by our characteristic impedance, so we can always use the same Smith chart. If our load and characteristic impedance happen to both be 50 ohms, that means they are matched and we would have a point at the origin. But depending on what the real part of our load impedance is, we can either move to the left or the right on this horizontal resistive axis. If we had a load impedance of 25 ohms and a characteristic impedance of 50 ohms, this would place us at 0.5 on our chart. So that's chill and all if we only have resistive loads that don't introduce any reactance element. But what happens if we have a complex load? Now we have to pay attention to the rest of the chart. Let's now take a look at the numerous circles scattered across the Smith chart. We have purely resistive circles in red. Taking a look at the circle labeled 1.0, if the real part of our normalized impedance is equal to 1, then our Zn value will fall somewhere on this circle. Like mentioned earlier, if there is no imaginary part of our normalized impedance, we would just have a point at 1.0. However, if our normalized load impedance has an imaginary component, we will need to use the reactance curves in blue in order to determine where our load impedance lies on that circle. Given the real and reactive circles present on our Smith chart, we can now map any normalized impedance on our Smith chart and use these impedances to find a reflection coefficient. Let's do a quick example. Load ZL and a characteristic impedance of 50 ohms. We first normalize our impedance so we can plot it on the Smith chart. We then look to see where our resistive circles and reactance curves cross. If we take a look at the red circle at 0.6 and the reactance curve that goes through negative 1.6J on our Smith chart, we can see there's an intersection on the bottom right plane of our chart. We can label this point 0.6 minus 1.6J as our normalized load impedance. Now, if you remember our reflection coefficient from earlier, we can use the Smith chart to find the magnitude and phase of the reflection coefficient at the load given our normalized load impedance. If you use a straight edge, you can draw a line from the prime center to our normalized impedance. The length of this line is equivalent to the magnitude of our reflection coefficient. Remember that the Smith chart is just another plot of the reflection coefficient in the complex plane, and that the grid of circles just represent the real and imaginary parts of the impedance corresponding to the reflection coefficient. To find the phase of our reflection coefficient, all we have to do is draw another line along the same straight edge until we reach the end of the Smith chart. There is a small strip along the outside of the Smith chart labeled angle of reflection coefficient in degrees. Looking at where the line goes through allows you to determine the phase angle of our reflection coefficient, which happens to be about negative 59 degrees. We can verify our result using the definition of our reflection coefficient from earlier. Using the Smith chart, finding the reflection coefficient using the normalized load impedance becomes quite simple. There are a number of other applications that go beyond the scope of this introductory video, and I've really only scratched the surface. I would recommend becoming familiar with the outside circles that tell us how many wavelengths away we are from the load or generator. These measurements allow you to find the input impedance a certain distance away in wavelengths from the load. You can also use these circles to design matching networks using quarter wave transformers as well as short or open circuited stubs. Last important information worth noting just to bring everything together. The unit circle on the Smith chart represents points where the magnitude of the reflection coefficient gamma is equal to 1, corresponding to lossless loads that are purely reactive, either capacitive or inductive, or extreme impedance cases such as an open or short circuit. An open circuit occurs at the very far right, where the impedance approaches infinity, while a short circuit is found at the far left, where the impedance approaches 0. At the center of the Smith chart, as previously mentioned, the reflection coefficient gamma is 0, indicating a perfectly matched load with no reflections. So you can tell gamma is equal to 0 at the prime center because when measuring the magnitude of gamma sub L, you always start from the center. I hope you learned a little more about the Smith chart today. It truly is an amazing graphical tool for all electrical engineers. Thanks again for watching this video, and subscribe for more content just like this.